Good afternoon. My name is Jean-Louis Briot. I'm a professor in the Department of Civil Engineering and the holder of the Spencer J. Buchanan Chair at Texas A&M University. Here's the program for this afternoon. First, I will introduce Professor Rozovsky. Then I will ask him to make some introduction remarks. Professor Biscontin will then introduce Dr. John Christian, who will deliver the 2003 Terzaghi lecture on the topic of geotechnical engineering reliability. How well do we know what we're doing? At the end of Dr. Christian's lecture, we will take questions from the floor. Then I will have the pleasure of introducing Professor Krizek, who will follow with his 2004 Buchanan lecture on the topic of slurries in geotechnical engineering. After a question period led by Mr. Darrell Hooper, I will invite Dr. Philip Buchanan, son of Professor Spencer J. Buchanan, to thank the speaker and give him the plaque. After a few photos, we will reconvene for a reception at my home. Maps on how to get to this place are at the entrance. Starting last year, the Buchanan lecture became part of a larger event, the Buchanan Conference. This conference starts on Friday morning and finishes on Saturday at noon. This morning, we had a series of presentations and discussions on the value of graduate studies. Tomorrow morning, we will have a presentation on our program by Professor Biscontin and all the other geotech professors, followed by the Geo Magic Show with Cassie Rutherford as Grand Wizard and Mike Linger as Apprentice Magician. The Buchanan Conference is aimed at recruiting more American and minority students in the geotech program at Texas A&M University. We have currently 34 graduate students, and 77% of them are foreign students. We do enjoy all of our foreign students, but we would like to reach a more balanced distribution. In order to try to remedy the situation, we have invited a few students from around the country and offered travel grants to help them out. Before I recognize them, I need to recognize the two co-chairs of the Buchanan Conference, Cassie Rutherford. Where's Cassie? Stand up and stay up. And Matt Miller. Where is Matt? Stand up and stay up. Now I would like to recognize the students that have come, that are the 5 visitors to our program. Noah Friesen, Colorado State University. Stand up, Noah, stay up. Anna Panova, Rutgers University. Where's Anna? Carl Vamos, Manhattan College. Christopher Zavatsky, University of Miami. And Amit Pandey, University of Arizona. Stay up. We've also invited our own A&M undergraduate students to come to the conference. If you're an undergraduate student at Texas A&M University, please stand up and stay up. Our graduate students also attend the Buchanan lecture. If you're a graduate student at Texas A&M University, please stand up and stay up. If you're a former student from Texas A&M University, please stand up and stay up. Now, if you're a friend of our geotech program here at Texas A&M University, please stand up and stay up. Now, I hope by now everybody's standing up. We really appreciate everything you do for our program. Now, let me take advantage of the situation to mention to you something that is coming up in the spring of 2005. Thanks to Dr. Roschke, our interim department head, and with the support of Dr. Rozovsky, our new department head, we're resurrecting the Geotechnical Engineering Case Histories course and the Geotechnical Engineering Board of Advisors. Those were two very successful concepts in the early 90s, and I'm very happy to see them back in place. If you wish to contribute by presenting one of your case histories to the students in the spring, or if you wish to be part of our Board of Advisors, the Geotechnical Engineering Board of Advisors, or both, please let me know. A bit of administration details. We no longer advertise the Buchanan lecture by a brochure in the mail. We send emails to a list of email addresses established over the years primarily from those who give us their email address in the guest book. This guest book is circulating. Who has it?
The sign-in sheet?
No, not the signing sheet, the guest book. Is it on the table, Richard? Okay, let's make sure that you sign that guest book. We'll circulate it in there. And we need your name and your email address if you want to hear about the next decision on the Buchanan lecture. You may also check the website listed on the cover of the Buchanan lecture booklet, which you found at the entrance of the room. The 2005 Buchanan lecture will be posted on that site in the middle of the summer 2005. Now let me call on Professor Rozovsky. David Rozovsky became the head of the Civil Engineering Department at Texas A&M University on October 1st, 2004. So I guess that makes him a freshman department head. David comes to Texas A&M from Oregon State University, where he held the Richardson Chair in Wood Engineering. His research interests include structural reliability and performance of structural systems, particularly with respect to wood. I've not known him for very long, but have already been very impressed by his energy level and his remarkable efficiency. I've asked Dr. Rozovsky to say a few words of introduction, including some background on himself and his vision of the future of the department. David?
Thank you, Dr. Brio. And ladies and gentlemen, thank you for inviting me to speak with you for a few moments this afternoon. It's a pleasure. I'm more than just a freshman department head. I am a newbie to the state of Texas. I have lived here and been working in the department for just under 2 weeks. So I am really quite new to the whole operation here. And if Jean-Louis is kind enough to say I'm efficient, it's because, quite frankly, I've had to be. I've had to learn an enormous amount in a short amount of time. And on top of everything else, my wife and I just had a baby 10.5 weeks ago. So I'm eager to spend as much time with them as possible. So I cram it all into about an 8.5-hour day. Jean-Louis asked me to say a little about my background. He gave you a little about where I came from. I was at Oregon State for the last number of years, where I held a chair in wood engineering, which is a very important structural material, wood, in the Pacific Northwest. And this was a unique opportunity because it was actually a chair that sat across two colleges, a College of Engineering and a College of Forestry. So it allowed me to try some fairly interesting and innovative things where we expanded some cross-cutting research across the colleges. We developed a host of new degree programs, graduate research areas of emphasis, and developed what I think is probably the leading program in timber engineering in North America today. We are very excited, Michelle and I, to come to A&M and to join the College Station community. And Melissa, although 10 weeks old, doesn't yet realize how excited she is, but seems to like the weather well enough out there. I want to just spend a few moments with you today and share with you some of the things that we're doing in the department that I'm really excited about, and also some of the things that might be of interest to the geotechnical community that's part of this broader family that is the friends and family of civil engineering at A&M. Two overarching themes under which all of our initiatives are going to fall in the next year or so are the theme of a culture of excellence, which is really a university-wide theme. You'll see this in A&M literature. You'll see this on their webpage. The university under President Gates' leadership is developing an emerging culture of excellence university-wide, and we'll adopt that obviously here in the Department of Civil Engineering as well. More local to our department, and something I think we're well underway in, is to promote and develop a community of scholars. This is a great department that is doing tremendous work in cutting-edge research, developing outstanding teaching programs, and quite frankly, developing a very good product at the end of the day, our graduates. We get along well, we play well with others. That's not always the case when you have a department of 55 or 60 faculty. This is a unique faculty among the large schools, and the ability for scholarly output is tremendous because there is so much cross-cultural interaction between the areas and disciplines of civil engineering. I'll tell you a little about some of the things that are going on in the department. You may have heard of the Look 100 Faculty Expansion Program. This is a program under which the College of Engineering gets 112 new faculty positions, and of those, 11 new faculty positions will come to the Department of Civil Engineering. That's not replacement positions. We'll hold those as well as people retire or move on. These are new positions to grow us to a level of activity and number of faculty that we had some time ago before there were reductions in programs. We have plans in place to grow all three of our graduate programs, the Master of Engineering degree, the Research Master of Science degree, and the Research PhD degree. We'll see through some innovative programs and some seed money to develop new research thrusts, an increase in the amount of collaborative work, not only across areas in civil engineering, but across colleges and the College of Engineering, and even across departments in the college and colleges elsewhere in the university. For example, there are some innovative activities that we're proposing now with the Bush School of Public Policy. Finally, through this and an aggressive marketing program that we've started now with both the communications office at the college level and the development office at the university level, we are going to be seeking an increased visibility on both the national and international stages. We have 5 new positions that we've just started to advertise for. In fact, if you get on ASCE's webpage, you'll see the electronic ad this week, and the print ad will come out in next month's ASCE magazine. We've also contacted all the department heads at the major programs to announce this to their faculty and graduating PhD students, postdocs, and so forth. What makes these 5 positions unique, at least in Texas A&M's history, is that they are not necessarily assigned to one area, but rather they cut across the traditional civil engineering disciplines and facilitate some of the things that I'm showing up here on this slide. And that's really the flavor of the department is one in which we try to break down traditional barriers, and we have a lot more activity between, say, the geotechnical area and the coastal area, or the ocean area, or the geotechnical and the structures area, and so forth and so on. This is clearly the future of the discipline. One of the opportunities that A&M has as a very large research program is that we have an opportunity to shape the future of civil engineering education, and it's our opinion that that will fall under these non-traditional barrier concepts. The 5 positions, one is in the area of advanced materials. We're also considering people with backgrounds and expertise in smart materials and structures. Another is an area called coastal or marine hazards. A third in construction engineering. A fourth in environmental biotechnology, and finally a position in infrastructure monitoring and assessment. Now, for those of you in the geotechnical area or considering practicing in the geotechnical area or studying at A&M, these 2 positions in particular might catch your attention. I've asked Dr. Briot to actually chair one of these search committees, and that's position number 5, and position number 2 is being chaired by Dr. Edge in our coastal division. We are actively recruiting applications from highly qualified geotechnical PhDs. I've mentioned the growth in the graduate programs. We are seeking, among other things, to place more of our PhD students in U.S. universities. This is obviously one measure of our success and something that we will be working actively to pursue. I'd like to spend just a moment recognizing some of the accomplishments of our geotechnical faculty, many of whom you've met already. But just in the last couple of years, in 2002, the Thomas Middlebrooks Award was presented to Dr. Albany for his paper on effects of disturbance of undrained strength interpreted from the pressure meter test. That is the paper that is the award given to the paper in geotechnical engineering selected to be most meritorious in the past year. Just this year, Dr. Biscontin received an NSF Career Award. These are extraordinarily competitive. Her award was for research in the area of characterization and modeling of marine clays for slope stability. We're very, very fortunate to have within our department 8 awardees of this NSF Career Grant. And finally, Dr. Briot was recently elected to the the governing board of the ASCE Geo-Institute, which is an honor and also a recognition of his contributions and leadership in the field. So we're very fortunate to have people like this on our geotechnical engineering faculty. I'll close by just saying I welcome you personally to College Station, to Texas A&M University. I hope we see a good number of you in our graduate program in the year or two ahead. And if I can do anything to help facilitate that, I encourage you to get in touch with me, and I'd be happy to meet with you. Thank you very, very much.
I am honored today to introduce to you Dr. Christian, our next speaker. The list of his accomplishments is very, very long, and I'm afraid that if I went through the whole long list, my speech would be longer or almost as long as his lecture. So you'll excuse me if I cut it short. He obtained his bachelor, master, and PhD degrees from MIT. He worked for Stone & Webster Engineering in Boston, where he raised to the position of vice president. And he's been a consulting engineer in Boston since 1994. He's a member of the National Academy of Engineering, an honorary member of the ASCE, and as you know, the 2003 Terzaghi Lecturer. He served as the editor-in-chief of the ASCE Journal of Geotechnical Engineering, and he's author of over 100 technical papers on a variety of topics. And reading his curriculum, I can say really a large variety of topics. It would take longer for me to say what these topics are than say, basically, he worked on everything possible in geotechnical engineering. He's also the co-author of 3 books, the latest of which is Reliability and Statistics in Geotechnical Engineering, for which effort I am very grateful, because I think geotechnical engineering future is that way, and it must have been a humongous task, and I'm happy he did it, and we can just enjoy the benefits of learning from his work. At this point, usually the person that gets this job that I have now says, and when John and I were in graduate school, and goes on with a funny anecdote from those times. Obviously, Dr. Christian and I were not in graduate school together. In fact, everybody here knows I'm a Berkeley graduate. I didn't go to MIT. We met for the first time last night at dinner, so I don't have any personal anecdotes to tell you. But I learned something last night, and what I learned is that today it's a bit more special delivery of the Terzaghi lecture for Dr. Christian, because his brother and his nephew are going to be in the audience. And so I would like to welcome them if they made it over here, or maybe we can welcome them later when they arrive. But without any further delay, please welcome Dr. Christian.
Well, thank you very much for those kind words. It's always a great privilege to be invited to give such a lecture and to be invited here. I should say that whenever you're asked to give a lecture like this, of course, after your first thoughts of gratitude and so forth, the question that goes through your mind is, what on earth am I going to talk about? And after a little discussion, we decided, well, maybe we ought to talk about reliability. Now, this raises an interesting problem, because this is a subject that falls between 2 stools. It's not really geotechnical engineering, and it's not really reliability. So I ask you to bear with me today. Those of you who are versed in reliability theory are going to find my treatment of reliability methods somewhat superficial. And those of you who are versed in geotechnical engineering are going to find there isn't really very much in the way of soil profiles and standard penetration tests and so forth. We're really kind of where these 2 areas overlap. I should also mention that my wife is a lawyer until she retired, and so is my brother and my nephew, by the way. I seem to come from a family of lawyers. And One of them, incidentally, is the county attorney in one county near Waco, and the other is the district attorney in the nearby county. So anyway, we went to dinner one night, and a man gave a talk on the rather complicated subject. In the car on the way home, my wife asked me what I thought of his talk, and I said, well, it was very interesting, but it had an awful lot to do with the time value of money and things like that, and it really cried out for a visual aid or two. He just talked for an hour. And she said, well, you have to understand, lawyers are very verbal people. They're not very happy with charts and tables and things like that. And then she stopped and said, but you guys can't even get up and introduce yourselves without showing a slide with your name on it and your address and everything. So with that, we'll show the first slide. Okay. Now, reliability, as you can see, has been a concern of engineers for some time. This event occurred in 1895 in Paris. One hopes the French railways have become somewhat more reliable since then. But clearly, this kind of situation has been of some difficulty for a long time. Let me also acknowledge a large number of people who have contributed to this subject of reliability in geotechnical engineering. This list is by no means exclusive. And if somebody is left off there, it's because of my ignorance and my error. There's no intention to leave anybody off or to insult anybody. But a large number of people have worked in this area, and I think we've had, I think we're going to have more in the future. I'd also like to acknowledge that there are two previous Terzaghi lectures which dealt with the issues of reliability and risk in geotechnical engineering, Arthur Casagrandi's lecture and Bob Whitman's lecture. Those dates, by the way, are the dates of the lectures, not the dates in which they were published, but they have been published, both of them, at least twice. Also, Suzanne Lacasse's lecture a couple of years ago dealt heavily with issues of reliability, although she has not yet written it up. It has not been published. Well, this is what I'm going to talk about today. First, I want to say a few words about the nature of uncertainty in geotechnical engineering. What is it? Where does it come from? What do we know about it? I want to touch briefly on reliability methods, although I really don't want to say a lot about that. That's the mechanics of the process, and that's been well written up. I then want to say some words about the meaning of uncertainty and probability, and about judgment and probability, and how all this works together in the conflict between intuition and analysis. I want to then say what I think is important in any of these analyses, and that is, what do you do with the results? That, frankly, is a problem in deterministic analyses as well. Some years ago, Professor Duncan and I had an argument in public on this subject, in which, because I had said that the most important person in a finite element analysis was the guy who would explain what the results meant. And he took issue with what I said, and some years later, he said, you know, you were absolutely right. I agree with you now. And I think it's true in this area as well. And then, of course, I have some conclusions. As we go along, I'm going to have pictures of some examples of what we're trying not to achieve, which is failures. This happens to be the right abutment of Malpasset Dam, which was a dam in France, many of you will know, not too far from the French Riviera. The reason why these failures occur is always the subject to a great deal of debate, but in this case it clearly seems to have been a failure to understand the importance of uplift forces in the design of the dam. If there's anybody who can be considered to be the father of probabilistic methods, it's Blaise Pascal. And Ian Hacking quotes him this way. I will read it to you. We ought to fear or hope for an event not only in proportion to the advantage or disadvantage, but also with some consideration of the likelihood of the occurrence. And basically, that's really what we're talking about here, that we ought to be considering not only bad events that might happen that we ought to design against, but how likely are these events to occur. Incidentally, when he made this statement, he was talking about being struck by lightning, but it applies in other areas as well. Well, we know that we live in an uncertain world. We know that there is uncertainty in geotechnical engineering. We know that the world out there is, we don't know as much as we would like to know about the world out there. So the question is, how do we deal with it? And there are several ways to do it. The first way is to ignore it. And Don't chuckle. This is in fact a widely used strategy for dealing with uncertainty. It is kind of a wing and a prayer approach. You hope that when the dam fails, you're not employed there anymore. That literally happened in one case. I will not mention names. There was a rather prominent dam failure, and the fellow who was the chief engineer of the outfit that built it had the good fortune or the wit or the luck to retire about a year before the dam failed. So when the congressional investigations started, this was a federal dam, he happened to be conveniently located somewhere in Arizona or something like that, and was not involved in the failure. So that's a good strategy for avoiding this kind of problem if you can do it. The second approach is to be conservative. Now, and of course, that's really what we often do. That's why we have factors of safety and so forth, is to make sure we are conservative enough. The problem is, how conservative is conservative enough? Clearly, eventually, you can be so conservative that it's impossible to build anything. And therefore, you have to, at some point, put some bounds on this thing. You will always have tremendous arguments about whether you have been conservative enough. So in geotechnical engineering, we have adopted and become attracted to what we call the observational method. And of course, you all know what the observational method is. You do the best you can in your design. You then make measurements. You correct, alter your design or your procedures on the basis of your measurements, and you keep on going. Terzaghi, by the way, called this the learn as you go approach. It was Peck, I think, who actually called it the observational method. This same technique, of course, has been adopted, or modifications of it, in many ways. The environmental community uses something called adaptive management, which is substantially the same sort of approach. You go along, you do your work, and as you learn more about the problem, you try to make adjustments, you adapt your approaches. What I'm going to talk about today is that maybe while we're at it, we ought to try to quantify the uncertainty. Now, this approach, the approach of using the observational method and quantifying the uncertainty, are not in conflict with each other. Obviously, one is a supplement to the other, so there's not a distinction there. But I think this is really where we should be going. Now, in his Terzaghi lecture, Casagrande gave this definition to calculated risk. He based this on a research of the literature, and I'll just read it. He said, "The use of imperfect knowledge guided by judgment and experience to estimate the probable ranges for all pertinent quantities that enter into the solution of a problem. The decision on an appropriate margin of safety or degree of risk, taking into consideration economic factors and the multitude of losses that would result from failure." And even though Casagrande did not discuss specifically probabilistic issues in his lecture, I think the definition is still one that we could live with and one that works quite well. Now, reliability-based methods have in fact been adopted in many areas of practice. I mentioned offshore platforms and structures. Jean-Marie Audibert is here in the audience, and of course, that's an area, as you well know, which has adopted reliability-based methods to a fare thee well. This lecture would be totally unnecessary in the offshore industry forum. But there are other areas which have seen the advantage of an explicit recognition of the nature of uncertainty. Dams, embankments, and levees, seismic hazard analysis. One of the difficulties with seismic hazard analysis is after all the probabilistic work is done, the results are usually then used deterministically, so we lose a lot of the benefits of the probabilistic work. Open pit mine slopes are increasingly designed this way. Nuclear waste repository studies are heavily probabilistically based. And then there is the vexed question of limit state design or load and resistance factor design, which has been widely adopted in the structural area, but which is a rather vexed topic in the geotechnical world. I'm not going to say very much about that, but I think it's a subject that first we have to deal with seriously, but second, I'm not so sure that just simply taking the structural approaches is going to work in geotechnical engineering. Another little interruption here. This is Vaillant Dam after the fact. What you have here is the Dolomite Alps, and this stuff here used to be up there, and it all came down, and there used to be a reservoir here. And the water in the reservoir went over the dam, which is on the other side of that little hill up there, and the water sloshed out and famously and went down the Piave River and killed about 3,000 people in a little village that was downstream of this thing. And there have been a lot of studies of this problem. Finally, some people have gotten some ideas about why the slide occurred, but at least as far as I can tell, nobody has been able to figure out why it was traveling as fast as it was when it hit the water. Clearly, this should be a concern to people building dams in the Dolomite Alps. Okay, let me say a few things about the tools that are available to us to do reliability work. There are the classic reliability analyses methods, first order, second moment methods, first order reliability methods, Monte Carlo simulation, and so forth and so on. There are event and fault trees. There are influence diagrams, and there are combinations of all of these. These, as I say, are well documented. There's a large literature on these techniques, and I don't think we need to spend a lot of time here today explaining how they work. The basic issue that we're getting at here is that if we have some way of determining or describing the load that a system will see and some way of determining the resistance, we know these things have some kind of probabilistic distribution, that the margin of safety is the difference between the two. We can also work with factors of safety, but let me work with margins for the moment. Now, it turns out that if these are distributed in any kind of reasonable way, this also must have some kind of a probabilistic distribution which we can work with. And we can, by various techniques, evaluate the mean and the standard deviation of that margin of error. Those reliability methods are ways of getting at those evaluations. And then we define something called a reliability index, which is simply the ratio between the mean and the standard deviation of the margin of safety. Now, exactly how we actually go about calculating those numbers is a subject of some that we could spend a lot of time talking about, but take my word for it, it can be done. Now, if the margin is distributed this way, it could be any distribution, by the definition that I just used, the distance between the failure condition, which is the condition when the margin of safety is 0, and the mean is simply beta times the standard deviation. And the probability of failure is the area there. If I now look at the cumulative distribution, this is simply the integral of that, then the probability of failure is the intercept, where this curve intercepts the vertical axis here. Now, I haven't said anything about what those distributions are. If, in fact, this thing is normally distributed, and that's a reasonable assumption for a number of cases, then it turns out that the probability of failure is simply equal to the cumulative distribution function for the standard normal variate evaluated at negative beta. Now that sounds like a big mouthful, and it used to be something that you had to interpolate. Nowadays, any spreadsheet worthy of the name has this as a built-in function and takes you less time to evaluate it than it does for me to tell you what it is. So you can get the probability of failure directly once you have the beta, the reliability index. Incidentally, I should mention that in some cases you will see people show this area here as the probability of failure. It's not. I'm not sure I know what it is, but whatever it is, that's not the probability of failure. Okay. We can also use event trees and fault trees. And I just want to say what they are. An event tree is a technique for looking at a succession of events. An event doesn't have to be something happening, it can be a condition. In other words, the existence of a liquefiable layer can be an event. And what you do is you create a tree. In this case, a rather simple one. You start with an event, and then you look at the things that could happen, and they have to be exhaustive. That is, they have to include all the possibilities. And they have to be exclusive. That is, they can't have any overlaps between them. And you determine the probability of moving from this position to each one of these. And you keep on doing that down here, and you get the conditional probabilities, then you multiply them all together, and that gives you the probability of winding up out here at the end of that train. You can do anything. You can analyze all kinds of things this way. I once did an analysis of the probabilities of winning a tennis match on the basis of the probabilities that an individual would win a particular point. Turns out very interesting that you get some counterintuitive results. Fault trees work the other way. Event trees go from left to right. Fault trees go from top to bottom. Fault trees start at the end, the dam breached in this case, and look at conditions that have to be satisfied for that to happen. And there are two kinds of situations that can exist. You can have a situation where both conditions have to exist before you proceed, or you can have a situation where any one of them, or more than one of them, can happen, and you proceed up that way. And there are mathematical techniques for working these things through, and you can combine event trees and fault trees, and there's a whole methodology here which can be worked out, and what it really is a way of forcing you to organize your thinking. This is a picture of Teton Dam in its full glory as it was ceasing to be a dam and becoming a flood. And this is another example of the kind of thing we want to avoid. Okay. Now, if we're going to apply these reliability-based methods, we have some requirements. And as always, there are 4 of them. First place, we have to have some input into this analysis. We have to have some methodology for doing the reliability analysis. We have to have some appropriate geotechnical analytical models, bearing capacity equations and that sort of thing. And we have to have some way of interpreting the results. Now, I've already said a few things about the methodology that we have for reliability analysis, so let's leave that alone. And I don't want to say anything about geotechnical analytical models other than to say that, in my opinion, the analytical models that are available to us as geotechnical engineers range from the excellent to the awful. Some of the models that we have, the analytical models that we have, are really, really bad and have really not been very well verified and have all kinds of built-in assumptions, and we use them without really understanding how bad they really are. Up there in the top of my list of things that really need some re-examination are the bearing capacity equations. But anyway, let's concentrate instead on the input first, and then we'll say some stuff about the output. Okay. First, I want to talk about the nature of uncertainty. Now, we've said things are uncertain. We know the world out there is uncertain. Okay. Now, what does that mean? And there are 2 kinds of uncertainty. These terms, aleatory and epistemic, I think were first used by a man named Hacking. There may be somebody else who thought them up. And they describe 2 different kinds of situation. The first, the aleatory, is the situation in which you're dealing with what you might call a truly random process. That is, the name, by the way, comes from the Latin word for dice thrower. And it is the situation that you have when you throw a pair of dice. Now, in the best of all possible worlds, if we knew the velocity of the dice and their angular momentum and the modulus of restitution of the table on which they're thrown, you could calculate, I assume, what the dice would show. But realistically, we know that's not the case. And in fact, in the language, when we talk about a throw of the dice or a crapshoot or something like that, we know exactly what we mean. Something that we have no way of predicting. It's really, really random out there. There's just nothing we can do to predict it. We can describe the randomness. We can say what the odds are of getting various kinds of dice, but there's nothing we can do to affect it. The second kind of uncertainty, which comes from the Greek word epistemic, which comes from the Greek for knowledge, has to do with the situation where the world out there is fixed. It is what it is, we just don't know what it is. And the example is the arrangement of cards in a deck of cards after you've shuffled them. Now, I can tell you exactly what the arrangement of the deck of cards is. All I've got to do is turn them over one at a time. Now, unfortunately, you don't let me do that when we play cards, but I could, in fact, tell you exactly whether it's there. There's no uncertainty in the arrangement of the deck of cards. The uncertainty is in my knowledge of the uncertainty of the arrangement of the cards. And I ask you to think a minute about how you play cards. Now, I assume some of you here play bridge, for example. And you will know that the whole thrust of the play of that game is to elicit knowledge, to elicit information from the bidding and from the play of the hand, so that a good bridge player early into the hand knows exactly where all the cards are distributed, because he or she has gotten knowledge, gotten information from the way other people have behaved. The same thing is true of poker, by the way. And you have reduced your uncertainty. You've reduced you've made your knowledge better by gathering more information. Now, the way you deal with these two kinds of uncertainty is very different. For this one, you can't do anything to reduce it. You can describe it, but you can't do anything to reduce it. This kind of uncertainty you can do something with, because the more information you have, the more you can reduce the uncertainty. And I submit to you that this kind of uncertainty is what we're dealing with, by and large, in geotechnical engineering. The geologic profile that we have out there is there. There's only one of it. And it's there, and it is whatever it is. The problem is we don't know what it is. And most of our efforts, or a lot of our efforts, are aimed at trying to figure out what's there. The second distinction that we need to bear in mind is the meaning of probability. Now, you can derive all of probability theory from three rather simple axioms. The only trouble is that nowhere does it tell you what probability is. It's just a thing, P. And so what do you mean when you say something has a certain probability of occurrence or of existence? Well, you can mean two things. The first thing you can mean is that it's a measure of the frequency with which things happen. I go out and I count things, like automobile accidents or something like that, or a number of times that teams that are 3 games behind in the American League Championship Series win the series and that sort of thing. And I then compile these statistics, and out of that I say, well, this is a measure of some underlying probability. There's something out there in the world that's called probability, and we're trying to measure it, and that's what we're doing. The second approach is to say, wait a minute, in most cases we don't have repeated experiments. If, for example, a few days ago we had a discussion of the probability of the Red Sox winning the World Series, we could have, that would be a meaningful discussion. Today, that's not a meaningful discussion. They won. You know, the probability of their winning the 2004 World Series is 1. They were successful. Furthermore, we're not going to repeat that experiment. And that's true of many things that we do. We don't have repeated trials. We only have one trial, or a small number of trials, and so therefore our probability is based really on a degree of belief about what is going to happen or what exists out there, not on repeated trials, and therefore there is no probability that lies out there that is a real thing that we are trying to measure. It's in our minds. Now, this all sounds very abstract, but let me point out something. Consider the insurance company. You go to the insurance company to buy insurance for something or other. The insurance company employs a building full of actuaries who are there to calculate the odds, the probabilities that you will die or that you will have an automobile accident or whatever it is that you're insuring yourself against. And they do this on a frequentist basis. In fact, if you go to the insurance company and ask them to insure you against something that they have very little experience with, they get very unhappy. They really don't know what to do with that. So the insurance company is a frequentist. On the other hand, you are a degree of believer. Because when you buy the insurance, you're insuring one life, yours. You're not going to have repeated trials here. You're only going to get one bite at that apple. And even if you're insuring something like your automobile, it's a limited number of trials that you're going to have there. You don't tend to have 15 accidents, in the next little while. You intend for this to be a very, very small sample. And so you buy insurance on the basis of your perceived needs, the needs of your family, what you would like there are all kinds of issues, obviously, that enter into your buying insurance. But you're buying it on the basis of your perceived need, which is your degree of belief in the probability against which you're being insured. The insurance company is a frequentist. You are a degree of believer for the same transaction. Furthermore, when we do soil testing, when we process laboratory data and we have frequency diagrams and means and so forth, we're being frequentist. When we're carrying out an exploration program, what we're really trying to do is to sharpen our degree of belief. Usually we start a field program with some model of what's going to happen out there, and as we get more data in, we modify that model, and we are acting as degree of believers. Okay. And finally, let me talk about the difference between frequentist and Bayesian statistics. The term Bayesian statistics has become very fashionable these days. Even the Economist had a section on Bayesian statistics about a year ago. You can use the term to frighten small children and other such things. Now, frequentist statistics are the kind of statistics that if you have taken a course in statistics, that's what you studied, probably. It's the kind of statistics in which you have null hypotheses and so forth. A subject which is mind-bogglingly confusing and which has a notation which I've often thought was intended not so much to help convey information but to prevent you from entering the temple. And anyway, what most people don't understand about traditional statistics is that and by the way, things like geostatistics and various kinds of regression analyses, discriminant analyses and so forth are all examples of standard frequentist statistics. And what you get out of this, if you say do a geostatistics evaluation of a profile, and you come up with certain probabilities, what those are is the probability that given the underlying model that you are trying to verify, you would observe the data. So it's the probability of observing the data given the model. Okay? Now what Bayesian statistics give you is the probability that the model is correct given the data. And I submit to you that that's what you really want. What you really want to know is the probability that there is, say, some kind of a fault or some kind of a failure mechanism out there that might cause trouble. You don't want the reverse thing. What is the probability of observing these data if the fault is there or if the model is there? In fact, this is a quotation from one of the many Bernoullis, who wrote, even the stupidest of men by some instinct of nature is convinced on his own that with more observations his risk of failure is diminished. And this is the essence of Bayesian approaches to reliability. Now I have here an example, and this is kind of Bayesian updating 101. It is the simplest example I can think of. It is an insult to anybody who's actually done Bayesian analyses, so those of you who are out there who have done them, bear with me. But it, I think, does illustrate some of the kinds of things that happen when you use this kind of approach. Let us suppose that we have, I should say also that this example is not entirely hypothetical. We actually had a case in which on which this is based. I think Jean-Marie may remember this incident, but I will not mention further what it is. Let us suppose that we have a soil profile out there, and we would like to know what is the probability that there are some zone or zones that are liquefiable. Now, that means by some measure we do CPTs or SPTs or something like that, and we're going to get some sort of a measure of whether this is liquefiable or not. And the question is, what is the probability that it exists? And how is this affected by successive borings? I go out and I make a boring and I get some information, and what does the next boring tell me that helps me to answer that first question? And finally, are more borings necessary? Well, let me assume the following. I'm going to assume that we're doing this with standard penetration test, and because of the configuration of the test and because of the way the zones are distributed and so forth, that there is about a probability of 30% of detecting the zones or zone in any one particular boring. That means there is a 70% probability of not detecting it in any one particular boring. Let me further assume that we all know that we can get false positives. By because the driller makes mistakes, we can often get low blow counts in standard penetration tests or in other kinds of tests. So there are situations in which we might get an indication of a weak zone even though it's not there. And so therefore, let's say there's a 5% chance of finding it even if it's not there. And there's a 95% chance, of course, of not finding it if it's not there. What this notation means is E means it exists, F means we find it, and the bar over the top means not. So this means the probability of finding it if it's not there. I understand finding, I guess, has to be in quotations in that situation. Okay, now let's assume that we have, I'm really neutral about this. I don't know whether the stuff is out there or not. So I'll say, well, all right, there's a 50-50 chance this thing exists. The probability that it exists is 50%. Now, and let's assume that I find it, or I get an indication that there is this liquefiable zone in the first boring. And this is the so-called Bayes' law. Again, you needn't worry about exactly how this gets derived, and it looks perfectly awful, but it really is fairly easy. It turns out that you plug in the appropriate numbers in this equation, and what it gives you is that if I detect it in one boring, I can then say that there's an 86% chance that the thing is really there. I'm getting to improve my knowledge a little bit. Let's suppose I don't find it in the first boring. Well, then I go through the same kind of analysis and I discover that there's only about a 42% chance it's there. In other words, I have reduced it from 0.5 to 0.42, but that's not very much. In other words, there's still a very substantial probability that there is a liquefiable zone there, even though I didn't find it in the first boring. And I can keep on doing this, and let's suppose we have 3 borings, and this is all the possibilities. You find it, and then you don't find it in the next boring, and you found it in the next boring, and so forth. Turns out it doesn't make any difference what order you do these things in. And you can see if I keep on finding it in the borings, why I get pretty darn confident that the stuff must really be there. If I find it in 2 borings, but I don't find it in the other ones, I'm still pretty confident. If I don't find it in any of the borings, my belief that it's there is reduced, but not nearly as much as you would think. I still have something like a 30% probability that there's a liquefiable zone there, even though I didn't find it in any of my borings. And in fact, you can do this for all the cases. We started with a probability of 0.5, and those are the results that we got after 3 borings. And there are 3 possibilities. We don't find it in any borings, we find it in 1, 2, and 3. And I think you can see that if you find it in all 3 borings, regardless of what you thought initially was the probability that it was there, you get to be pretty darn confident that it really exists. If on the other hand you don't find it in any borings, the amount you deviate from a straight line inclined at 45 degrees is pretty small. In other words, not finding it in 3 borings doesn't really buy you all that much additional information. I submit to you that this is the kind of thing that happens a lot in our construction projects, that we find, we all know of nice surprises that have happened during construction, even though we had very nice boring programs and very nice exploration programs. The particular instance I'm thinking of, they had the entire excavation dug before they found out that they had liquefiable soil underneath it, and the Frankie Pile Company was delighted because it was the largest, densifying that stuff was the largest Frankie Pile job in North America at the time. Okay. All right. Another little interruption here. This is the St. Francis Dam the morning that it was filled to capacity, or the morning before it was filled to capacity. This is what it looked like the next morning. That was, there's still arguing about why that dam failed, but clearly that was not what was intended. Okay, let's say a few things about how we go about getting soil properties. Now this, we've all seen pictures like this: index property, field vein, and so forth. And in this case, we have 3 zones: a marine clay, a lacustrine clay, and so forth. Now, let's concentrate for a moment on the field vein strength that has been measured. And I submit to you that if you had to choose the field vein strength that you would use for the marine clay, that you would probably choose some sort of an average value through there, and you'd be pretty happy, pretty confident with using that number for your analyses. On the other hand, when you come down here to the lacustrine clay, you've got a problem, and that is that, yes, you could put an average through there, but it would, there'd be a lot of scatter around there. You'd have to accept a large uncertainty in that value. So you could put maybe some kind of an inclination, a slope in there, or maybe even some sort of a higher order curve through there. Now, if you put some sort of a higher order curve, a curve with more parameters to describe it, you would reduce the scatter about the curve, about the values that you're using. But you would also increase the uncertainty in the parameters that you're using to describe the variation of the strength. In other words, you'd be much more confident of the location of a mean value than you would if you put some sort of a curve through there. So the trade-off between the two kinds of description of this error, between the systematic error, namely the location of the mean, and the scatter about that error, is a trade-off. You increase one at the cost of decreasing the other. Furthermore, and this is, I think, the important point, this is not an aspect of nature. It's a modeling decision. How I choose to model that stuff is a choice I make. The data come from nature. But to say that, suppose I put a uniform, I assumed that there was a mean value and that's what I'm going to use as a uniform value and there's a certain scatter about it. And somebody else says, no, I'd rather use a more complicated description of that variation and I'm going to have a smaller amount of scatter. The difference between those two statistical descriptions are purely modeling decisions. It's not that nature has changed between those two. I made the decision as to which of those two I would like to do. And so a lot of these choices we make that lead to descriptions of error are modeling choices, they're personal choices, they're not the result of nature. And this chart has been around for a while. When you look at the uncertainty in properties, it really comes from, there are 2 things you can divide it into. One is data scatter and the other is a systematic error, which is what we just discussed on the previous slide. This is the mean trend, or then this is the scatter about that trend. And these can be further broken down into the real spatial or temporal variation. And then there's always random testing errors, which you'd like to get rid of. They're small scale errors, and there are techniques for doing this. The systematic error can due to a real statistical error in the trend. That's something that happens when we do any measurement. And then, of course, there's bias in measurement procedures. You'll notice those data that I had before were field vein data, and we all know we have to correct those field vein data on the basis of plasticity index. And those data can vary a little bit from that correction itself has a lot of uncertainty with it. So there's a certain element of that enters in here. Now, what's important here is that this kind of error propagates all through the system. If I'm doing a bearing capacity analysis or a settlement analysis or a slope stability analysis, those errors propagate all through, and they're with me all the time. This kind of error tends to average out. If you do, for example, a slope stability analysis, And if you look along the failure surface that you're using, that the strength may be high or may be low, it kind of averages out over this. So this kind of error tends to get averaged out in our analyses. This kind of error sticks with us. And it's important to separate out the two, even though it may be the result of a modeling choice. Now, let me say a few more things about measuring properties. Let me say that I have measured the shear wave velocity of a deposit, and I get these numbers. Now, if I calculate the mean and I calculate the standard deviation, that's what I get. Now, there's kind of an assumption that we make when we do this that these things are normally distributed. They may not be, but let's say that they are. Now, I haven't told you the whole story about this. These are not real data. What these are is 6 values of shear wave velocity that I generated with a random number generator because I was trying to look into something else. And I generated them from an underlying normal distribution. This happened to be the first 6 that I generated. And the properties of the underlying normal distribution were that the mean was 240 meters per second and the standard deviation was 24. Or if you want to see this in a picture, this is the distribution I generated them from, and this is the distribution that's implied by the means and the standard deviation of the data that I got. In fact, when I first got them, I thought I must be doing the random number generation wrong, because this was so far from that I had a hard time understanding. No, this is what happens. If you only have 6 data points, you are going to have trouble. You are sometimes going to encounter cases in which the implication you get from those data are not really very good. And so when if out in nature there is something that's normally distributed and you only measure it 6 times, you got a really good chance of getting it wrong. There's 2 guys who became rather famous, Kahneman and Tversky, and some years ago they wrote a paper in which they talked about the law of small numbers. You probably have all heard of the law of large numbers, which says if you go out and measure things and take a lot of measurements, eventually your measurements will converge on the underlying distribution. The law of small numbers is that people like to believe it also applies when you've got small numbers. And of course, it doesn't. So be warned, unless you are collecting hundreds of data points, you're going to have problems like this. Now let me talk a little bit about expert elicitation and expert judgment. We all know what experts are. We are experts. You know, we get asked questions about things and we give pronouncements on things, including trivial things. But there's a large literature on this subject. A lot of people have looked into how good experts are. Now this is a case, a fairly well-known case actually, in which there was an embankment north of Boston, the I-95 embankment, which was abandoned. And the idea was that they were going to go out and they were going to pile more dirt on top of this thing until it failed. And they invited 7 experts, and these folks were really well-known guys. And they were asked to give a bunch of estimates about what was going to happen. And one of the things they were supposed to predict was how much additional fill would be necessary to bring this embankment to failure. And they were also asked to give 50% confidence limits on their estimates. In other words, they were supposed to tell the people running the program an upper and a lower bound, and or an upper quartile and a lower quartile boundary, and that they would say that if they expected that 50% of the time the actual result would fall within that range. Now, the actual amount of dirt that it took to fail that thing was 18.7 feet, and that's what this thing is here. This dotted line here is the average of the best estimates, which are the red dots. And you'll notice that the average of all 7 experts is pretty good. In fact, what's really critical in this case is not the incremental amount that it took to fail it, but the total height of the embankment. And so the experts did a pretty good job, on average. However, notice that in no case did the actual amount that it took to fail the embankment fall within any expert's 50% confidence limits. the actual amount that it took to fail the embankment did not fall within any expert's 50% confidence limits. Another example. Now, this is a case in which 9 designers were asked to design foundations for transmission towers. And then there were 6 foundations designed, six of these foundations. And then each of the foundations was failed, and in this particular case, the pull-out load is the important load, and so these were pulled out. And for each expert, they calculated the mean of the ratio between their predicted capacity and the actual capacity. Notice that if this number is less than 1, that means the expert was conservative, because P over Q is less than 1. And the red dots here are the averages of all 6 for each expert. And the lines are the bottom and the top. And these are arranged in this order because the paper from which I got this happened to arrange them in order of decreasing goodness. And so that's why there's that trend. Now notice that these 2 fellows did pretty well here. They tended on average to get things pretty well. Notice, however, even this guy who was ranked number 1 by the folks who wrote the paper was about 30% conservative in this case, and about 20% unconservative in his worst case. So he had a pretty healthy range of goodness in his estimates. You might also ask what separated these guys. Well, it turns out that there were all kinds of different things. This fellow here had a master's degree. I guess that's in view of our meetings this morning, that should be an encouragement. He also had a lot of experience, and he had in fact participated in a similar program some years before, in which they had made some predictions and then actually tested things. This guy, however, had 30 years of experience and basically nothing else to bring to the table. So, there wasn't too much difference between them. And then there were all kinds of various other things over here. I should point out that these folks down here tended to be the ones that had master's degrees and nothing else. So education all by itself clearly wasn't the thing that made you a better expert in this case. But clearly there's a real issue here about how good experts are in making this kind of an expert. Clearly people tended to be unnecessarily conservative if they made any kind of mistake. Okay, let's just summarize this by saying that spatial and systematic variances reflect a modeling choice and have different effects. That the values computed from small samples can be misleading. And that experts tend to be more confident than they should be. They tend to underestimate the variance in their estimates, how far apart. And this is true across the board. It's not just geotechnical experts. It's even people who estimate the scores of next Sunday's football games. Their experts tend to be a lot more confident than they really ought to be. And this gets us to the subject of engineering judgment, which we are all in favor of. However, it seems to me that we put ourselves in a really dangerous situation if we simply use engineering judgment as a word, as a pair of words, and don't base it on evaluated experience. In other words, if it's not based on actually going out and looking at what's happened the last time out and changing one's opinion on the basis of observations, engineering judgment can be a really dangerous thing. And a word of warning, I noticed my 2 lawyer relatives are in the back of the room there. I would not recommend that you use the phrase engineering judgment in a courtroom unless you happen to be prepared to defend yourself against the opposing attorney. In other words, it can be a euphemism for speculation or guessing, and you really don't want to be in that position. Here's another little interruption. This is the Old Man of the Mountain. It's in New Hampshire. It's on their license plates. It's on their quarter, or at least it was, because one day they came to work, and that's where it was. Okay, let's say a few things about interpreting results. And out of all this analysis, we get a probability of failure, and I put failure in quotation marks because failure can be a lot of things. It can be excessive settlement, It can be any kind of unexpected bad behavior, and so we know what we mean by failure. And the first question is, what is the allowable probability of failure? Well, if you go to the public and you say, gee, what's the allowable probability of failure? It's 0, or very, very small. But that's not really a very realistic thing, and so we need some handle to deal with this. And one way to do it is to use what's called an FN plot. Now, this is Greg Becker's FN plot, and so Greg once said that this plot is the most widely replicated thing he has ever used, and every time it's used, it's in somebody else's paper, so he never gets credit for it. But anyway, what's done here is that people have looked at he has looked at various kinds of failures. And he's looked at the dollars lost and the lives lost. Now, unfortunately, this kind of implies a dollar value of a life, and that's not really what he intended to do. And then looked at the annual probability that these events, that this sort of failure would occur. And you notice that this thing this is a log-log plot, so there's a lot of scatter in it, but you notice that what you tend to find is that things that have low costs tend to have higher probabilities of failure, and things that have high costs tend to have lower probabilities of failure. And they fall kind of along a trend here. Now, you'll notice that these are his data, so if you have questions about it, you have to ask him. But for example, when he did this, he found that supertankers and mobile drill rigs were somewhat more risky than the general trend of this thing. Commercial aviation was way down here. We all know commercial aviation is a great deal safer than almost anything else that we do. And so this kind of gives you an idea of where to fit in one of these probabilities of failure. You can look at the probability of failure and what the cost might be and see whether this fits in with what is generally, with this kind of a trend. Now, I would argue that this kind of a trend really represents what society has decided it's willing to accept. Other people will disagree with this, but the very fact that we do this and we build dams and foundations and mine pits and so forth, with these observed probabilities of failure and cost of failure, suggests that we as a society, kind of a society writ large, are willing to accept this kind of thing. Now, you can do interesting things with this. For example, we have had 2 failures of the space shuttle over a period of about 22 years. Each one killed 7 people. And that's about 0.1 failure per year. And 7 people means that space shuttles are kind of up here, which suggests getting on the space shuttle is a very risky proposition. And something that maybe should be done by trained astronauts who presumably are aware of this sort of reason. It does suggest that maybe we shouldn't be encouraging school teachers to get onto these things. Although it also suggests that maybe we should continue the politician in space program. Now this kind of insight has been used by a number of people. This is the Hong Kong Planning Department. They have a version of this. In this case, it's fatalities versus the number of events. The Netherlands people have another version of the same sort of plot. The Australia, New Zealand dam people have a version of this plot. And each one of these, the idea is that you give this to the designers and say, look, you go through one of these reliability analyses, and if you find yourself down here, you're okay. If you find yourself up here, that's not okay. And if you're in this region here, well, then you have to go back to the drawing board and do a little more thinking about whether you're really willing to live with that. Current thinking is that these really shouldn't be very bright lines, that there should be a kind of a fuzzy zone in there. And also, these are somewhat old plots. They've been updated recently. But this kind of thinking has now permeated a number of regulatory and design agencies. Now, there are certain problems with absolute probabilities. The first problem is that the one thing that is not considered when you do one of these risk analyses is all the things you didn't consider when you did the risk analysis. And if you look at failures, you discover that, of course, an awful lot of them occur because of something nobody thought of. Obviously, if you didn't think about it when you were doing the design, you're highly unlikely to think about it when you do the risk analysis. So there's a lot more risk out there that you didn't consider, and so therefore, these probabilities are probably lower bounds. Professor Rosofsky was telling me at lunch today that there is a new kind of in a reliability or uncertainty in addition to regulatory and epistemic. It's called ontological, which is this issue, the uncertainty due to what we don't know, due to what we ignore. Okay. The second point is that people have a lot of trouble with small probabilities. There's a lot of evidence to suggest that folks are able to deal with things up to or down to maybe about 1 chance in 10. And once the probability gets lower than that, they have not the foggiest idea what that means. And I don't mean just the public. I mean engineers, scientists, nobody can deal with probabilities that low. And you need some mechanism like the ones I was just showing you in order to deal with them. Well, this suggests that maybe another way to deal with these things is to look at comparative probabilities of failure. And this is an example. These were 3 dikes, 3 designs for dikes. 6 meter, 12 meter, and this 23 meter was a multiple stage dike. The idea was that we're going to build the first stage, let it consolidate with drains in there to improve the strength, and then build the rest of it. And the question was, well, what were allowable factors of safety and what was going to happen here? Well, if you did one of these reliability analyses, you discovered that the expected values of the factors of safety were these numbers. Again, we all know that we shouldn't believe these numbers, the second decimal point there. They're all kind of substantially the same result. However, the probability of failure that's calculated from there is very different. This has a probability of about 2 times 10 to the minus 2, and this one is 7 times 10 to the minus 4. This one has a great deal lower probability of failure than the other ones do. And the reason is the failure is so broad that all the spatial uncertainty averages out over it. You can do some mathematics on that if you're willing to make some assumptions about how the standard deviation of the factor of safety varies as you change parameters. You can change those around so you can say, well, now look, let me look for some target factors of safety there. 1 chance in 1,000 of failure is probably something we can live with for an embankment, a dike, for a structure like that. These are much smaller structures. We can fix them pretty easily, so maybe we'll live with a probability of 1 in 100 for those. But failure of this guy would be a real mess, and so we want to make maybe 1 in 10,000. Well, if we work those through, we can then find out what the target factors of safety, the target expected factors of safety are for these 3 different designs, and these are the numbers you get. Notice that they are in exactly the reverse order of the expected probabilities of failure. A very counterintuitive result, but one that in fact comes out of the mathematics. And another thing we can get out of this kind of approach is contributions of different components. The same problem, this is the 23 meter high dike, and there are 6 contributions to the uncertainty here. The strength of this, the intact strength of the clay, the 2 clays, the strength after they were consolidated due to the drains, the friction angle of the fill, and the unit weight of the fill. And the bars, the blue part is the systematic error, the contribution of the systematic error to the variance of the factor of safety. This part up here is the contribution of the spatial error, and the reduction from there down to there is due to the averaging effect over the failure surface, which I told you is substantial in this case. Now notice, what this tells you is that you really want to look at the strength of the clay, this lacustrine clay, intact and consolidated, and the unit weight of the fill, amazingly enough. It turns out that those are the things that are really contributing to your uncertainty and therefore to your probability of failure. You really don't want to waste your time looking at these other 3 guys. Even if you've got them nailed down completely, it's not going to help you very much. So if you're now looking at where should you spend some money to improve things, to get a better feel for it, the analysis tells you where you ought to go and is a real guide to you in future work. Okay. This is the Chuquicamata open pit mine. That thing is about 800 meters deep. It is a big hole in the ground. And it's got, there's a fault that runs right through the middle of it. And you can see that the slopes over here look a lot better than the slopes up there, and that's because of the dip. The material tends to dip this way, and also there's different material on both sides of the fault. And in designing these things, by the way, you can see little things like that. Those are monster mining trucks, you know, those big things that you don't even let on the highway. You can't even see the pickup trucks that are here. This thing is unbelievably big. And they use, routinely now, are using reliability methods in order to design these slopes. You want them to be as steep as possible, for economic reasons. But if you make them too steep, you're going to bring them down. Okay. Let me conclude then by I've had several conclusions to this talk as I went along, but I want to end with a few points that I'll try to leave with you. First is that probability is not a property of the world, it is a state of mind. It is something, it has to do with the way you perceive the world around you. And second, that geotechnical uncertainty is primarily epistemic, it's Bayesian, and it's belief-based. And those are what we have to use in order to deal with it. And finally, I think the current challenge to us as a profession is how to use probabilistic methods in practice. And in some areas, like the offshore world, that's already happening, but I think we need to, that challenge faces us as a profession. And I end with a picture of the La Conchita slide, which we used as the cover of our book. This is the slide, and I suspect the folks down here had a lot more belief in geotechnical unreliability after that thing came down in their neighborhood. And I think that's all I have to say. And if there are any questions, I'll try to answer them anyway.
I have a request, actually.
Yeah.
I think that we should talk about probability of success rather than probability of failure.
Well, yeah, but that's about 99 and a bunch of decimal point with a lot of nines after it. People have as much trouble with that as they have with the small numbers.
But I think psychologically, it feels a lot better.
Yeah.
The minute you tell a client there's a probability of failure of, he may not even hear the number, he senses that there's a probability of failure.
Sure, and well, there's a wonderful story told about this, that some years ago, two guys and a girl actually, did a study of dam failures. This is not long after the Teton Dam failure. And they looked at the historical record for dam failures. And they conclude, and turns out there are records all over the place, although they're hard to dig out. And they concluded that the probability that any one dam would fail in any one particular year is about 1 in 10,000. So, in other words, there's about these are engineered dams we're talking about. It's a lot higher when you're talking about something that was just thrown up by the Boy Scouts last week to make a new lake. And this has some very interesting implications, because if you're doing a cost-benefit analysis for one of these dams and somebody comes along and says, by the way, there's a chance of 1 in 10,000 every year that dam is going to fail, it knocks the cost-benefit calculations into a cocked hat. So they discovered, by the way, that the Bureau of Reclamation had just about exactly 10,000 dam years when Teton failed. There are a lot of other data out there to support this. So they presented these results to the Office of the Chief of Engineers, who were, as you can imagine, although they'd paid for the study, they were not really delighted with these results. And they were, in fact, furious. So after these results were presented, one of the senior people there said, well, what this shows is that the dams we've built are perfectly safe, and now they're even safer. So that's the ignoring the uncertainty approach.
Any other questions?
Would you make some comments about the failure of the Waco Dam? I think your relatives are from Waco, aren't they?
Well, they're right up there. They probably know more about it than I do. I really don't know anything about this.
It was a Corps of Engineers dam.
Yeah.
And they missed a formation, and I believe it's called the Pepper Shale. Mm-hmm. And it got wet during the construction, and the whole sucker failed during the construction. Mm-hmm. And Casa Grande got involved, and it went on and on and on. And it was all over poor exploration. Sure. Or that was what the conclusion was.
Well, as I said, that little example that I gave about the borings, the liquefaction, is based on an actual event. What actually happened in that case was that we'd sent a guy out in the field, and we'd had a blowout at the foot of one of the sheetings. And he was sent out there to see to it that we fixed that. And he had a drill rig out there, and he wanted to see if there were any other cases there might be a problem. And he said that the last day I was there, the driller was going to go off the site, and I said, you know, I'd better take this hole down to bedrock, because sure as hell if I get back in the office and I didn't run the boring all the way down to bedrock, I'm going to get criticized. So he took the thing down, and the next sample that he took, he hit low blow count material. And we stopped the job, and no, it was, all hell broke loose. And we had experiments, tests, borings, all kinds of stuff all over the site. And nobody had detected it before. So it's a real problem. There's a very interesting book. It's the 1987 volume of the journal Engineering Geology. The entire volume is devoted to this. And it's the proceedings of a conference that Jerry Leonards ran at Purdue in 1985. And the subject of the conference was the failure of Teton, Baldwin Hills, Vaillant, and Malpasset. And that was close enough in time to those failures so that the people who'd been involved in both the design and the construction and the evaluation of those failures were still around. And so they had all kinds of presentations about it, and they transcribed the whole thing verbatim. And it is an absolutely fascinating document. So you want to see raw psychology out there on the page with people defending their decisions and trying to explain how come they really knew what they were doing, even though this dam is now a pile of rubble downstream. It's there. It's really, really a fascinating volume. Worth getting your hands on if you can do it.
Now it is my pleasure to introduce the 2004 Buchanan lecturer, Professor Raymond Krizek. Professor Raymond Krizek is professor and holder of the Stanley F. Pepper Chair in the Department of Civil Engineering at Northwestern University. He received his Bachelor of Engineering in Civil Engineering from Johns Hopkins University in 1954, his master's degree in Civil Engineering from the University of Maryland in 1961, and his PhD in Civil Engineering from Northwestern University in 1963. In 1963, he accepted a position of assistant professor at Northwestern University, where he rose through the ranks and became professor in 1970. In 1980, he became chairman of the Department of Civil Engineering, a position he held until 1992. His research and consulting interests include soil structure interaction, buried conduits, groundwater flow, disposal of slurry wastes, grouting, soil cement, pavement subbases, dredged materials, and the engineering properties of soils. Professor Krizek has published over 300 articles in journals and proceedings, and is the editor of about 10 books. Among other awards, he received the Huggentugler Award from ASTM, the Walter Huber Prize from ASCE, the Terzaghi Award, and the Wallace Hayward Baker Award from the Geo-Institute of ASCE. Professor Krizek was the second president of the Geo-Institute of ASCE. He was elected to the National Academy of Engineering in 2001 and became an honorary member of ASCE in 2002. He has been chosen as the 2006 Terzaghi Lecturer. He's also a registered professional engineer. The title of Professor Krizek's Buchanan Lecture is Slurries in Geotechnical Engineering. Professor Krizek.
Thank you very much, Dr. Briot, and good afternoon, ladies and gentlemen. It's a pleasure to be here to share this afternoon with you. Similar to John Christian, I have to remind myself who I am and what I'm going to talk on, and with that, we'll be off and running. Got to time myself here. Geotechnical engineering encompasses problems ranging from rock mechanics to slurry mechanics, and perhaps even one step further to suspensions. For those of you who think this may be about slurry walls, it has nothing to do about slurry walls. It's other kinds of slurries, so you can put that out of your mind. Most geotechnical engineers deal with the broad range of soils, sands, silts, and clays, and mixtures thereof between these two extremes, rock and slurries. And they're typically concerned with constructing foundations on or in these soils, tunneling through them, or building earth dams with them. For reasons that were not part of a master plan, much of my career has been spent working with slurries or suspensions. So when invited to give this talk, I chose this subject because it is one that the average geotechnical engineer has had relatively little experience with, and hence might provide some interesting thought-provoking outlooks. Following overviews of how most industrial slurries are generated, the material properties of slurried wastes, the general approaches to the disposal of slurry waste, the presentation will focus primarily on research studies undertaken at Northwestern University over the past 4 decades on 5 different slurries. Actually, it's going to be 4 because subsequent to the talk I had to reduce it and I'm going to eliminate 1. And the major lessons that we can learn from these studies. The intent is not to delve into the details of these individual studies, but rather to provide simply enough background to enable one to understand the general nature of the problem and then to share as succinctly as possible the lessons that we have learned. The slurries were very different in nature and the purposes of the studies were quite varied. You see the ones listed. The one I'm going to eliminate is flue gas desulfurization sludges. Each of these studies spanned a number of years, more than a decade in 4 cases, and involved quite a few talented students who are listed in the back of the paper, about 50 or 60 of them. First, I want to talk about the generation of waste. Most slurried wastes are generated by processing an ore and extracting from that the constituents of interest, be they gold, silver, copper, iron, whatever. To better understand the nature of the waste produced, it is helpful to have a basic knowledge of how the ores are processed to remove these minerals. Although the extraction process may vary considerably with each individual ore, certain steps are fundamental to most ores. At the heart of most milling processes are crushing and grinding the ore, after which the various techniques are used to remove the minerals of interest. Crushing is usually produced in stages to reduce the size of the rock so that it can be fed into grinding equipment. Primary crushing typically reduces the rock to fragments on the order of a half a meter or so, and then secondary crushing gets it down to maybe a couple of millimeters. Then grinding is primarily by ball mills or rod mills to further reduce the size of the particles that were obtained by crushing. Grinding is the final operation in the physical reduction of the ore, and the final gradation of the depends on the particle breakdown of the hard rock and the clay content in the ore. Since the particles produced by grinding will vary in mineral content, the goal of concentration is to separate those particles with high mineral value from those with no value. This is usually accomplished by gravity separation, magnetic separation, or froth flotation. Leaching involves the removal of minerals from the ground particles of an ore by direct contact with a solvent, usually a strong acid or an alkaline solution. Leaching may also change the properties of the tailings, and it often leads to environmental problems. Heating either the slurry or the ground is another process. It's sometimes used to extract minerals, such as the extraction of oil from oil sands. The final step in the milling process is to remove some of the water from the slurry before it is discharged into the disposal area. After the thickened slurry is deposited in an impoundment area, coarser particles settle into supernatant water with reagents, and colloidal particles is collected whenever possible and returned to the mill for reuse as processed water. What is left in the disposal area is a high water content, soil-like waste material which must be further dewatered in some fashion. In some cases, wastes are generated by a cleaning process, such as cleaning the sulfur dioxide from the stack gases of electric power generating plants burning sulfur-rich coal. And the most common technology for doing this is a variety of flue gas desulfurization processes which generate a waste slurry by scrubbing or absorbing the sulfur from the stack gases. Okay, at this point, I want to review with you some of the reasonably well-established engineering property relationships that govern the post-depositional behavior of these slurried wastes. Indices and properties are compared with a variety of materials over ranges that extend well beyond those normally encountered in conventional geotechnical engineering practice. When considering a dilute suspension of suspended particles, the term void ratio, which may be on the order of 50 or 100, makes little sense, and a preferred term is solids content. The term void ratio becomes meaningful only when the slurry becomes a soil or a soil-like material. This occurs at the end of sedimentation and the onset of self-weight consolidation, or when the particles come in contact with each other and initiate the transfer of effective stress. Now, this value is termed the zero effective stress void ratio, or sometimes simply the initial void ratio. And it provides the origin for measuring strains in the material at any point throughout its consolidation history. Although it's rather simple to define this, it is very difficult in practice to determine exactly when that occurs. Indications are that it is when the water content is somewhere in the vicinity of 5 to 7 times the liquid limit. Virtually all mathematical models describing the consolidation or desiccation of these wastes are strongly dependent on the determination of this initial or zero effective stress void ratio and the relationships among the effective stress, void ratio, and permeability. When a thin slurry or suspension is deposited in a containment area, the ensuing densification process occurs in 3 stages, as indicated here. The duration of each of these stages is highly dependent on the characteristics of the slurry or the suspension, and the demarcation between these stages, again, is usually not well defined from a practical point of view. This figure shows a plasticity chart with approximate ranges for the liquid limit and plasticity index for a wide variety of clays and slurried wastes. As can be seen, the values of these materials plot slightly above the A line in the zone typically characteristic of highly compressible materials. The compressibility of various fine-grained waste and a few clays for comparison is summarized in this figure. These materials span an enormous range in compressibility, with void ratios from about 20 to less than 1, and may involve material behavior at much lower effective stresses and much higher void ratios than, again, normally encountered in geotechnical engineering. Of all the components that comprise the problem under consideration, the permeability relationship is arguably the most important and the most difficult to quantify. Except for a few models that incorporate experimental values directly, experimental data, or use the coefficient of consolidation, all others require a relationship between the permeability and the void ratio. Permeability values for a wide range of waste materials and 2 montmorillonite clays are summarized in this figure. Note that this graph spans 8 orders of magnitude for the permeability, and from essentially impermeable to approximately the permeability of silt, with the waste materials spanning somewhat more than about 4 decades. Several researchers have developed methods for estimating the permeability from constant rate of deformation consolidation tests, or by back calculating it from the results of seepage-induced consolidation. Remember, we're in this slurry stage where these normal terms consolidation and such are suspect. In some cases, the magnitude and rate of consolidation can be obtained from empirical relationships, such as one like this, and there are a variety of these in different books and so forth. This one was stolen from Vic, I think. Or a graph like this, which is something that we developed and is pretty good up to a void ratio of about 2. You get a lot of random scatter beyond 2, but up to about 2, that line up the middle is not all that bad. That's the compressibility to C sub C, if you will. Slurries and suspensions are often modeled as Newtonian or Bingham fluids, the mechanical behaviors of which are depicted by curves A and B in this slide. In such cases, the viscosity is defined as the slope of the tangent, or sometimes the secant to the curve, of shear stress versus strain rate. And the yield stress is defined as that stress below which no flow occurs. However, both of these are really just approximations for sake of tractability, because in reality, most slurries are neither Bingham nor Newtonian and are more defined by curve C. This brings us to mathematical models for large strain consolidation. Although analytical models comprise the heart of most predictive techniques for the rate of settlement, the physical process to be assimilated is often not adequately understood, and the complexity of the governing natural phenomena usually dictates the incorporation of several simplifying assumptions to achieve mathematical tractability. The major assumptions in conventional consolidation theory are generally recognized as being excessively restrictive for analyzing the large volume changes manifested by these waste slurries. The two most popular approaches to circumvent this restriction utilize either the incremental small strain or finite strain theories. Incremental small strain models maintain the simplicity of classical Terzaghi type consolidation theory and constitute the next logical step to extend its applicability. And the solution simply involves dividing your deposit into layers and then satisfying continuity at the interfaces between the layers. Where the finite strain formulations result in nonlinear second-order partial differential equations using material rather than spatial coordinates. While this is complicated mathematically, it does have a lot of advantages. In both cases, however, a zero effective stress void ratio is needed to initiate the process. The changes in the void ratio and permeability with effective stress are very large. In the early stages of consolidation, the effect of seepage-induced consolidation can be very important. Not only self-weight consolidation, but seepage-induced, the very fact that water is flowing down. Secondary consolidation may be regarded as simply that portion of the settlement response that is not described by some appropriate theory of primary consolidation. In other words, primary consolidation is what it is. We all know that. Secondary is may be regarded as simply that which is left over. In our discussion of dredge materials later, we will see that many long-term consolidation tests manifested tertiary consolidation. And I'll save that comment until we get the graph later on. Next, I want to review with you many of the concepts that have been used and should be considered when challenged with a slurry disposal problem. These are listed on this slide, some 18 of them, and we'll discuss each one briefly, one by one. Now, only a few of these may ultimately be applicable to whatever problem you have under consideration, but at least one should consider each one of them explicitly. First is process modification. When addressing a problem of waste disposal, often not considered in sufficient detail are the modifications that might be made to the process by which the waste is generated in the first place. This is especially true for geotechnical engineers because we are usually too quick to accept the waste in whatever form the chemical or mechanical engineers in charge of the beneficiation process provide them. However, many times a frank discussion with everyone involved will show that some modification of the waste generation process at the plant will improve considerably the handling and disposal properties of the waste materials generated. The design and construction of the dikes enclosing the waste for an impoundment area comprise a substantial portion of the cost of the disposal operation. And it's always desirable, if possible, to use the waste material to construct the dikes. However, water retention dams, like the one shown here, are best suited for tailings impoundments with high water content requirements. You hate to do this because it's a lot of upfront cost. Alternatively, raised embankment dams, like the one shown here, are desirable and staged over the life of the impoundment, using material little by little. Next is liner design. Liners are inherently high cost and are usually used only when the situation involves high toxicity waste or stringent groundwater protection requirements. Typical liners consist of clay or various geosynthetic materials. Since the dewatering process is strongly dependent on the length of the drainage path for the escape of water, as we all know, it may be highly advantageous in some special cases to install a drainage blanket and associated dewatering system at the bottom of an impoundment area prior to placing any waste. Many wastes contain sufficient quantities of sand or sand-like material that can be separated first and used to construct such a blanket. In addition, a wide variety of geosynthetic materials, although expensive, are also available for this purpose. When a low solids content waste is pumped into an impoundment area, the first process that occurs is sedimentation. Accordingly, it's the particle size distribution of the solids in the suspension that controls this. While a dispersing agent is used in a laboratory hydrometer test to determine the particle size distribution, one must remember that dispersing agent usually is not added to the field material as it is dumped in the waste disposal site. So don't be confused about running a laboratory hydrometer test and then predicting settlements on the basis of that. Retention time. Very often the supernatant water from the sedimentation in the impoundment flows over a weir and back into the water course, or is collected via a drain system for reuse as processed water. The degree of clarity that is achieved in the supernatant water depends on the time available for the particles to settle from suspension, and the disposal area must be designed to reflect this. On the other hand, if higher clarity is desired in the effluent, portions of the surrounding dike, like such, may be designed to act as filter elements, or you may include cartridges, such as these, in the overflow weir process, so the water flows after the sedimentation through the cartridges before it goes back into the water course. All these, of course, are added expense. The objective of the thickened discharge method of disposal is to thicken the tailings water mixture such that it behaves as a viscous mud rather than a liquid slurry. Under such conditions, the material will form a conical pile with side slopes of a few percent, as seen in this slide. Advantages of this method are basically the elimination of impoundment dams and a few other measures. However, the cost savings realized by eliminating the impoundment dams may be largely offset by the higher cost of construction and operation and the greater expenses associated with pumping this thickened mud. Dry stacking, which we'll talk about later when we talk about bauxite ore, is a modified version of the thickened discharge method, and it is suitable in areas where the evaporation rate is very high. In a typical scenario, a dike encircles the impoundment area, and a pipeline with discharge ports every few hundred feet rest on the dike. Disposal begins by opening one of these discharge ports and allowing the slurry to form a tongue extending at a slight slope from the dike toward the center of the impoundment area. After the tongue reaches a depth of perhaps a meter or so and several hundred meters in toward the center of the dike, the valve is closed for that area and the next one is open and the process is repeated. This process continues for perhaps 30 or 40 valves around the dike, around the pipeline encircling the dike. And by the time you get through one cycle and you're back to where you started, in an ideal world, the first tongue of material deposited should have desiccated to a rather low water content, at which time a new tongue, a second tongue of material is placed over the first, and so forth. You do the same thing again. And so the major limitation of this method is that the climate of the region must be such that each layer will dry sufficiently in the time that you have available before an overlying layer is placed. Dry disposal via vacuum filtration. In an even more extreme case of reducing the water content of the waste at the plant, the dry disposal method endeavors to remove much more of the water from the waste before it is placed in an impoundment area. This is usually accomplished by vacuum filtration using a drum or a belt, and the tailings come off the drum or belt as a cake, if you will. Since the capital and operating costs for vacuum filtration are very high, the method can usually be justified only when the filtration is an integral step in the ore processing operation, but not when it is supplemental. It's a supplemental dewatering method that is added to the conventional thickeners. Furthermore, although the tailings are in solid form, when handled and placed in the disposal area, their water content is still usually 20 or 30%, which is higher than optimum water content for compaction and will usually result in near saturation of materials at the void ratios you end up with. The loss of water from the surface of a tailings pond is a two-stage process. In the first stage, the conductivity of water is sufficiently large that water loss is controlled by the prevailing climate, such as radiation, air temperature, wind speed, humidity, and so forth. And results are comparable to those measured in pan evaporation tests. During the second stage, the converse is true, and evaporation losses are essentially independent of the environment. When the overlying free water is decanted, evaporates, or drains through the layer into the underlying soil, the surface begins to desiccate and a crust is formed. The formation of a crust has both advantages and disadvantages. The advantages are increased strength and density of the material. The disadvantages are that it inhibits further evaporation. Nature often provides the first solution to this problem by the development of alligator cracking as shrinkage occurs in the desiccating crust. And this provides channels for the horizontal movement of water and additional surface area for evaporation. To overcome the impedance of a crust, the evaporation process and consequent dewatering of the waste, various techniques have been utilized to agitate or break up the crust. Disc-like or plow-like tools are often pulled across the surface via cables operated from the dikes. And in one particular case, this riverine utility craft, Corps of Engineers military vehicle, was used to break up the crust. This is a scene from down in Mobile. For some types of materials conducive to the growth of vegetation, near-surface dewatering can be accomplished by vegetation, and the dewatering is accomplished by transpiration through the leaves and the root systems. Plants transpire large quantities of water during the growing season. The rate of water loss may actually exceed that of free water evaporation, and will endure long after the surface has become dry. In addition, vegetation can assimilate minerals and various organic toxic compounds, and much of this material can be removed by a timely harvest of the vegetation. This slide shows volunteer vegetation at several disposing sites along the Maumee River in Toledo. These are sites where we worked. That grew up perhaps in just 1 or 2 years. It's an agricultural watershed, so it's probably particularly conducive to growing this kind of vegetation. Surcharging, a familiar process to all of us, is a time-tested procedure for accelerating consolidation and dewatering, and increasing the rate of strength gain. But the low strength of these materials usually makes it difficult to apply the surcharge without causing a stability failure and a consequent mud wave. Also, the long times involved preclude the use of this procedure except for certain special situations. The use of wicks to accelerate drainage, of course, can reduce substantially the time required, but there's usually a problem with equipment access over these materials. So, this may be a somewhat new one, spraying and sandwiching. Spraying involves the use of a floating pipeline equipped with a nozzle to sprinkle sand over the surface of soft tailings. This is used often with the phosphate slimes down in Florida. The sand slowly sinks through the tailings to form vertical channels, somewhat like sand drains, which together with the added overburden of the sand serve to relieve pore pressures and accelerate the dewatering. And here's an example of such an operation in functioning. This is one of the phosphate slime pits down in Florida. Electroosmosis. The first limitation of electroosmosis is the relatively narrow range of materials, primarily silts, over which it is effective. And the second limitation is that except for very special situations, the power consumption and associated cost are prohibitive. Storage capacity. The storage capacity of a given impoundment depends to a large extent on the final dry density and the rate at which that density occurs. And we'll see some examples of that later on. And the final step in this quick overview is reclamation. Current environmental regulations dictate that virtually all sites must be reclaimed and placed into productive use. And while productive use is a generally accepted goal, the term means different things to different people, and that can cause a lot of problem. As always, closure is not possible until the materials deposited are considered to be permanently stable and environmentally innocuous. Similarly, there are cases where cost for permanent stabilization of abandoned tailings are orders of magnitude greater than all the ore ever taken from that site. A typical cost of reclamation may be on the order of several $1,000s per acre, and government regulations commonly require the posting of a reclamation bond at the outset to ensure that the reclamation efforts are carried out after termination of the disposal operation. And this brings us to the point where we're going to talk about the 4 different slurries. The first is clays. In this particular case, we knew that the directionally dependent mechanical properties of clay soils, in other words, the anisotropy of clay soils, are governed to a large extent by their structure, or microstructure, which consists of complex combinations of particle arrangements and interparticle bonds. The geometrical aspects of particle arrangements at a microscopic level is usually termed fabric or microfabric. And fabric, together with the time-dependent interparticle bonds, is termed structure. Although structure is actually the primary characteristic that controls the engineering behavior of clay soils, fabric is an important component of structure and is much more amenable to study and evaluation. Accordingly, that's what we did. Depending on the physical and chemical conditions that prevail during deposition, an intrinsic fabric is imposed on natural soils. In general, this intrinsic fabric may range from highly random to highly oriented. And subsequent to deposition, the application of stresses causes a stress-induced fabric. That is, as you run a test, you induce changes in this fabric, changes in the intrinsic fabric. Summarized here are the major results of a long-term research effort. This was about a 10 or 12 or more year effort to relate in a quantitative manner the microfabric of a kaolin clay and its mechanical properties. This was accomplished by preparing block samples with preconceived fabrics, which were controlled by the appropriate combinations of pore fluid chemistry and consolidation stress paths. And the consolidation stress paths are either isotropic or anisotropic. And isotropic consolidation was achieved by placing the clay slurry in a balloon and subjecting it to a hydrostatic state of stress with drainage ports at two diametrically opposed points. During the entire process of anisotropic consolidation, pore pressures and lateral stresses were measured. Upon completion of the anisotropic consolidation, and while the clay was still subjected to its ambient consolidation stresses, horizontal and vertically oriented vane shear tests were conducted. And this was all accomplished in a slurry consolidometer. All this looks easy. It took us maybe 5 years to finally get to this point. This is the slurry consolidometer. You'd start out with it filled about up to there, and by the time it finished, it was maybe 4 inches or 5 inches of clay. And this is where the veins were put in, so forth, at the end. Okay, then, after that was done, then the consolidation stresses were released, the clay blocks were removed, the mutually orthogonal specimens were trimmed, and creep test, traxial test, and uniaxial compression tests were conducted on the samples that you trimmed. And finally, a comprehensive appraisal of the clay fabric at its various levels of organization was obtained by examining each sample by the combined use of scanning electron microscopy, optical microscopy, and X-ray diffractometry. Although each individual method, each of these methods, was shown to provide a correct appraisal for the general nature of the fabric of each sample, a synthesis of the information from these three independent procedures has the advantage of characterizing the fabric at different levels of organization, ranging from almost nanoscale, if you will, up to something about 1 or 2 millimeters. Here is an example of the form in which we presented the data. The upper right simply describes the test conditions. The upper left is the data from the X-ray diffraction test, and it is something that can be quantified. You can actually put a number on that by some appropriate analysis. The two pictures in the middle are the scanning micrographs. That gives you a physical feel, visual feel for the nature of the particles in mutually orthogonal directions. And finally, the bottom group of figures is the optical microscopy work, and that's done on thin sections, sections trimmed by a microtome and then looked at, and you get either illumination or extinction, depending, and it's something like photoelasticity, if you will. So this was done on all these various samples, many, many different samples. And this, in a sense, was one of our pride and joy, if you will, that we were able to produce, and believe me, no simple task, to produce these very, very different fabrics. In the top two photographs, you see this is a picture. The upper left is looking down on the sample, and you see pretty much all plates, clay plates. And the upper right is looking in on the sample from the side, and you see pretty much all edges. So we got a very oriented fabric. The lower two is a random fabric. You look at those two pictures, and you really don't see much difference between them. So it took many, many years to get that sort of thing. So we got those extreme fabrics. Now, a little bit about the results. During the process of anisotropic consolidation in that consolidometer, the direct measurement of vertical stress, lateral stress, and pore water pressure provided a unique opportunity to determine K0 throughout the consolidation history as the clay consolidated from a slurry to a block. Now, at the outset, it was anticipated that K0 would decrease from unity, and namely hydrostatic stress. It was a slurry. So we thought it would be hydrostatic stress at the beginning, to about 1/2 when consolidation was complete. Okay, and perhaps this would be somewhat, the rate at which this happened would be somewhat dependent on the fabric. However, despite the existence of well-documented different fabrics, which I explained previously, results of the experimental program manifested no identifiable relationship between K0 and clay fabric during loading. And K0, furthermore, K0 was constant throughout the whole daggone process and equal to about 0.7, plus or minus 0.05. So that was a little bit of a surprise to us. The use of the effective friction angle, a la Ireland and Yanbu and so forth, to determine K0 turned out to be quite practical, though, quite good. Okay, in the triaxial test, vein crest, and creep shear test, the effective fabric was manifested to a much lesser degree than we expected. Horizontally trimmed samples were stronger. As sample that you trim this way and were stronger and less deformable, but the differences were typically on the order of maybe 10 to 25% and an occasional 50% or so strain. Furthermore, the random samples were somewhat stronger than the oriented samples. And this suggests that the anisotropic behavior that many of us talk about from time to time of clays is really dependent on the interparticle bonds and not just the fabric. Because we did a pretty good job with fabric here, I think, and it in many ways was somewhat disappointing that we didn't get larger differences between horizontal and vertical directions. But that's life. Okay, that brings us to dredged materials. That's the next kind of slurry. The need to protect the ecology of the Great Lakes and other waterways of the United States led to a variety of problems concerned with the dredging and disposal of increasing volumes of polluted dredged spoil in areas of high population and industrial development. A normal method to dispose of this is an impoundment area, as we've talked about before. So during the first half of the 1970s, we undertook a very comprehensive study, both laboratory and field, to try to evaluate the time-dependent development of strength and so forth with the dredged materials. Although sediments from several Great Lakes harbors were studied, most of the research took place at 4 disposal areas along the Maumee River near Toledo. And you see them here. These, there's one, this one, and the Iowan site, which you can hardly see out here. Those were, by the time we got there, those were filled. And we did a lot of work. Pen 7 was a new site. It took them 2 years to fill it, and we were able to follow this site from onset right through the end. And it turns out even 30 years later, we went back. The filling of these sites is indicated here. They were filled from 64 up through 74, but the top when you see Pen 7, the 72 through 74, those are the years that we monitored Pen 7. One important thing that we determined is that, as you would expect, the materials deposited in each of these sites is essentially the same. So we could consider all 4 of these sites as just one big thing. So we, and that helped a lot when we synthesized the data. We put it all together. This slide shows you a few properties of the soil. It's rather organic. Sand, silt, and clay are pretty much in the proportions of 1, 3, and 2. 1 part sand, 3 parts silt, and so forth. And it, for all practical purposes, it was an organic silt is what we had to deal with. This figure shows the test results from a standard primary consolidation response. Well, it shows that a standard primary response curve was measured from up to about here. And then this is the secondary portion, up to about 10 to, that's a week, up to about a week. At which point we got this, unexpected. That's what I call tertiary consolidation. So it's quite a deviation from the secondary. Here's the primary here, and then the secondary, and then this. This test ran for several months. This is not unique. We found this, we ran the test some of them a long time, somewhere as long as 9 months. Both conventional consolidation test and slurry consolidation test. And this curve, this type of curve, was not at all uncommon. It's not a artifact of the testing technique or anything. That's why it happened. So your guess is as good as mine. It seems like some sort of breaking of interparticle bonds as the strain rate gets to a certain point. But it would also happen at different increments of load. That would happen, you put the next load increment on, you get another curve that look, pretty much, and it's not negligible, it's pretty darn large. So that happened a lot. This is an interesting sequence of slides. We determined the coefficient of permeability for these materials from a variety of methods. You see in the upper right-hand corner here. And the range is a pretty big range, 10 to the minus 4 to 10 to the minus 9. Void ratio goes from 10 to 1. And you see where most of the data fall. And that looks like John could treat that with statistics, perhaps. However, this slide indicates something that makes you think it's the same data, except for 2 points down here. Those are 2 field tests, permeability tests. So it makes you wonder what all this data from the lab is worth when these are the 2 field tests we got. So be careful, be careful. Consolidation, desiccation. We developed in this process a one-dimensional mathematical model to describe the desiccation consolidation process. And this model has the capability of predicting the water content and the settlement response of a landfill at any given time after deposition. And the calculated settlement predictions turned out to be pretty good agreement with the measured at Pen 7. This is at 3 different points, 3 different locations down here. This is the point, the first part of it is where it was really a slurry and you couldn't get out and determine anything. That was the first year, in effect. The second year, we were able to get out on it a bit. Storage capacity. I mentioned that earlier. This number looks real simple, but it's one that we kind of had a unique opportunity to determine because we were able to measure the topography of that Pen 7 area before any dredgings were deposited and then after they were deposited. And the ratio between the bin measure volume, which is what they measure in the hole of the dredge when they scoop it up out of the channel, and the disposal area volume was about 0.62. That's a good number for determining the capacity of the storage area. Now it's still going to get smaller than that. It'll still densify more. And that's seen in this figure, when we sort of synthesize all this data and put it together, the numbers in parentheses are number of samples, over at least 8-10 years, that's the curve we got, which showed that it was densifying about 4% a year. And that's obviously is not going to continue forever. But now, about 30 years later, this was in the 70s, a couple of years ago, we went back to 3 of those areas. We didn't get out to the island, but we went back to 3 and tried to look at the effect of aging. Now, aging in this context is 30 years, not geological time, if you will. What did 30 years do to the sample? The changes in shear strength are those changes which are not attributable to changes in density or water content or partial saturation. You eliminate all those, and then the additional change in strength must be then attributable to aging. At least that was our rationale. So, and the results showed that the strength gain was somewhere around 21 to 36 kPa, which is between 40 and 70% of the measured 30-year undisturbed strength. And the undisturbed strength after 30 years was more than an order of magnitude higher than the 1-year strength and about 2.5 times higher than the 5-year strength. Those are just some relative figures. Now, another further analysis showed that the 30-year values for the dry density and the water content appear to be reaching their equilibrium values. But the shear stress will likely increase for many years. That is, the curves for the first two were kind of leveling off, and your shear strength showed it was like so. So it looks like it's going up here somewhere. Bauxite residue. Red mud, or bauxite residue, is obtained by using the Bayer process to remove aluminum from bauxite ore. Many parameters influence the chemical and physical properties of the bauxite residue. And the process parameters are usually adjusted at the plant to optimize the yield of alumina and the recovery of caustic soda. And little or no effort is expended to control the properties of the red mud. Hence, the properties of the red mud may vary tremendously from plant to plant, and even within a given plant, and even at a given plant within a given day. It's very hard to do a research study when that's happening. Red mud is highly thixotropic, and its rheological properties are strongly dependent on the chemical composition and the flocculent dosage. When discharged in the field, red mud has a pH on the order of 12, and the index properties of a clayey silt. The true grain size with the dispersants and all of the bauxite residue is about 1/10 of a micron. But one can easily measure 1 or 10 microns. It depends on the flocculent dosage. So in 1984, thereabouts, we, together with Alcoa, investigated the feasibility of dry stacking. That was the method I described before, to dispose of thickened bauxite tailings. And we did this down at Point Comfort, Texas, so not too far from here, I guess. I described that process before, so I'll skip right over that. That's what we attempted to do. And here's the result. The dry stacking process, so those were the pipes. They weren't on top of the dike, they were on the side of the dike, but that's the idea. You'd open that valve and the material would begin to flow. Okay, this is the topography of that valve. Would be located right here, if you will. And that's the beach, as they called it, before the mud began to flow. Okay, we'd gotten out there first and put stakes over with elevations and so forth and so on, because after the mud started to flow, we had to observe everything from the dike. And then you open the valve, and now the mud begins to flow, starting at the upper left, this one, and then this one. These are 3 different times during the process, and this 4th one is when the process is all over. And the black dots are all where we had driven the stakes. So we determined the elevation, how far it flowed, and so forth and so on. And the net result of all this was that limit equilibrium can predict reasonably well the final configuration of the red mud to within 25%. Now, maybe you don't think 25% is good, but it looked pretty good to us at that point. We ran 5 of these flow tests, and they all were pretty consistent and gave that result. At the time this work was undertaken, around 1980, microfine cements, or sometimes called superfine or ultrafine, were relatively new in the United States. Japanese were using them, and the only cement you could get was Japanese produced at that point. In the past 2 decades or so, the availability of these cements and our experience working with them has increased tremendously. Now, microfine cements have particle sizes that are typically about an order of magnitude smaller than the particles of ordinary Portland cement. And this is obtained by further refinement of Portland cement by either milling further or ventilation, like collecting fly ash. However, due to their high manufacturing costs, they're very expensive and used only in special situations. Now, their particle size distribution, however, makes them very beneficial for permeation grouting. As you can see in this slide, the top part, that's the microfine cement grouts, and they're quite comparable to a whole bunch of chemical grouts. The chemical grouts have undergone some flack from time to time about toxicity and polluting the ground and so forth and so on. So there's an advantage there, and compared to chemical grouts, they're not that awfully expensive. They certainly are expensive compared to Portland cement grouting. They're quite good for these specialized applications, so for fine fissures or perhaps even finer sands. One problem is they tend to compact in dry form, due to humidity and electrostatic phenomena, and when wet, they tend to flocculate. Well, to offset that, you need a dispersing agent for that purpose. Now, when designing a grouting operation, field engineers are concerned with several different properties of candidate grouts, not all of which are mutually independent. Suspension grouts, such as this, are usually characterized by their water-cement ratio, which is determined by weight. There's a set time. The set time, there are two stages. If the set time is too short, it's impossible to inject the grout very far into the formation. And if it's too long, it may be diluted or elutriated before it sets in place. And the second set time is after it's in place, how long does it take to firm up and become a cohesive part of the formation. The bleed rate, which is really the rate of sedimentation, is important because we'll see an example of that in just a moment. You don't want the grout, the particles, to settle within the pore of a soil before it sets up. So you don't want a high bleed rate. The viscosity controls the rate at which you can inject the grout, and the yield stress controls the distance into the formation that you can inject the grout. The role of high-energy shear mixing in cement grout technology is widely accepted. One can argue about, however, what high-energy shear mixing is. High energy is one thing, but maybe shear mixing is different. To compare, to investigate this, the effect of shear mixing, that is, we prepared some grouts with 1-to-1, 2-to-1, and 3-to-1 grouts in different mixers and mixed them for 1 to 10 minutes. The different mixers you see listed there. The first one is a standard field coldcrete mixer, which some of you may know about. The second is a custom designed proprietary mixer, only one of a kind in the world, I guess. And the individual who owned it claimed that this was the only true shear mixer. Shear means you're really shearing the particles, splitting them apart. The other two were, the third one was just a household blender. The fourth one was a paint mixer, if you will, for mixing paints. And the last one was not a high energy mixer, but just a paddle mixer. So we tested those, and now what did we find? Well, we found a lot of things. I can share just a few with you. In the case, for example, of bleed volumes, we got 40 to 60% difference in the bleed volume, depending on which mixer you used. Yield stress, which is kind of important. We got factors of 10 to 20, depending on the mixer that you used. So it's important, but the profession knows it. It's not a big discovery. Perhaps the discovery is the order of magnitude of some of these differences. And this becomes particularly important when you're extrapolating lab tests to the field. We've got totally different mixers. So what you're finding in the lab, again, maybe like the permeability test, may have little or no relationship to what you're doing in the field. In addition to viscosity and yield stress, at least 4 other factors strongly affect the injectability of a microfine cement grout. These are mechanical filtration, chemical filtration, product variability, and reaction with the host medium. Based on size relationships alone, a lot of injection criteria based on that, you should be able to inject a microfine cement grout into a sand with a D10 on the order of 100 to 200 microns. A lot of times you can't do that, however. So it's just something, it's more than just the size criteria. This is a very interesting one, chemical filtration. Because of the colloidal nature of the cement particles, very, very fine particles, they're conducive to chemical filtration, which means as the grout is moving along, it is adhering to the side of a sand particle. And we indeed have column tests that we did in the laboratory where the effluents from the column, you're pumping the grout in one end and you're collecting the effluent at the other end. And we've determined that for the right chemistry and so forth, the coarser particles actually pass through the sand column and the finer particles are captured. That's what I referred to as chemical filtration. Product variability, this drove us crazy for a while. Small variations in a product. You get several bags of cement and you're running a lab, you use up one and you open another. And you could grout using this bag of cement, we grouted the sample. You try to repeat the test with a different bag of cement, and the damn thing won't work. Okay? What we ultimately found out is oftentimes there was maybe only 0.5% or 1% of a coarser sized particle, something that might be just 4 or 5 times the mean size. It was just a small percentage of the coarser particles, which, because we were trying to work with the limits, of course. So they would blind the pores and then presumably collect some of the finer particles, and that's why you couldn't grout. And finally, reactions with the host medium. This is simply the soil the host is of such a chemical nature that trying to pump the grout in causes some adverse chemical reaction that you really don't want. And that becomes particularly important when you're trying to use this to capture, to block off a plume or to encapsulate some sort of contaminant in the sand. Anisotropy. After injecting the grout in the sand, the cement particles which are not trapped in the intergranular contact points or do not adhere to the particle surfaces begin to settle. And this is the bleed part of it. And the bleed water accumulates in the top portion of the pores. Now for 1-to-1, 2-to-1, and 3-to-1 grouts, we determined that the pore was filled about 98% filled with hydration product for a 1-to-1 grout. Well, it's a pretty thick grout, 1-to-1. On the other hand, for a 3-to-1 grout, it's only about 2/3 filled, 65%. Okay, and that's going to play a role in the next thing we talk about. So, and that produces an anisotropy. So that's depicted physically here. And you see this is just the void. Here's the fluid grout. That's what that's supposed to depict. And here it is. It's settled. The grout has settled in the pore, and this is open pore. You haven't got the pore filled with the grout. Okay, now we looked at that with a study by grouting Ottawa 2030 sand with, again, a variety of grouts. Well, I mean, one kind of grout, but a variety of water cement ratios. And the description of this test, we talk about horizontally cured and vertically cured specimens. Well, perhaps I can jump ahead and show that. We ran ultimately 3 different kinds of tests. The top one, permeability, the middle one, unconfined compression test, and the bottom one, a bending test. That is a moment with 2 moments, if you will. In each case, you grouted the specimen with the grout 2-to-1, 1-to-1, whatever it was. In one case, you leave the specimen this way. This is vertically cured. In the second case, you do it this way and let it cure. Okay, so in other words, the grout's going to, because of its bleed, its sedimentation, the grout is going to get to the bottom of the pore in a different way. And so after it's all cured, now you run the test. In all cases, the tests are run in a long column. So now you got mutually orthogonal, and let's see what we get. Interesting. Okay, here's a table that depicts the permeability values. If you look at the 1-to-1 grouts and the top portion of the 1.5-to-1 grouts, we couldn't measure. They're less than 10 to the minus 7, and with the technique we're using, we can't tell anything, to be honest with you. Okay, if you look down at the 3-to-1 grouts, okay, those are all some different numbers up front, but that doesn't matter. The whole reason for doing a permeability test is to get the right exponent. They're all 10 to the minus 2. So there's not too much difference between the 3-to-1 grouts. Well, those are the ones with a lot of voids. So it doesn't matter too much whether you're this way or that way. But look at the ones, the 2-to-1, for example. Now you got 2 orders of magnitude, and even 2.5-to-1 as well. You got 2 orders of magnitude. I mean, this one is, where are we? That one is 10 to the minus 7, well, that's here, just go down. 10 to the minus 5, 10 to the minus 3, 5 and 3, this one's 5 and 4, 4 and 2. Big difference, 2 orders of magnitude difference. And this is also particularly important. When you grout in the field, you get vertical curing, but the water flow is usually horizontal. So if you run a test in the lab, grout it vertically, let it cure vertically, and then run the test vertically, you're 2 orders of magnitude off. Okay, unconfined compression test, that's the left-hand slide. Well, the curves look pretty close together, but if you look real hard, you'll see a difference. Well, let's see, the horizontally and vertically cured specimen, you see, for example, that this, what's that, the triangles, let's say, look at the 28 data. The triangles are here, I think it's 35% higher. But there is maybe not a tremendous difference, but they're higher. Here, these are tensile tests. That's as deduced from the bending thing. This one, I know, is 35% difference, and this is 135% difference in the tensile strain. Whether the specimen is, that's for a 3-to-1 grout, whether the specimen is horizontally or vertically cured. So at this point, you've probably heard more about slurries than you ever wanted to in your lifetime. So it's probably good that most of you are still awake. As you can readily appreciate, however, they present to our profession an array of problems every bit as challenging and interesting as the more traditional problems with which you normally deal. Predicting the time, the settlement of slurries is subjected to self-weight consolidation, and in some cases seepage consolidation and desiccation is an extremely challenging problem, and it encompasses new developments in mathematical modeling, laboratory testing, associated interpretations, property formulations, and the whole bag of tricks. And at the end, experience dictates a cautious approach to simple empirical extrapolations. Determining the solution will involve a consideration of a broad range of alternatives, including a generous portion of engineering judgment. We've heard that term before. And it's a student, at the session with the students, I quoted this little Peck quip, if you will, about 10 or 15 years ago. There was a bunch of students talking with Peck, and he was talking about engineering judgments. And the students were, of course, concerned, how do you get engineering judgment? And Peck says, it just takes experience. The student says, well, yeah, but how do you get the experience? He says, poor judgment. So you gain experience real fast, unless you can learn from somebody else's poor judgment. This is kind of interesting, I think. Even though a correct prediction does not necessarily validate your model, makes you feel good, but the complexity of the many factors involved suggests that you might get the right answer by a fortuitous combination of all these things that you have to put into it. So you got to be careful. Even though you get the right answer, you may not have all the pieces correct. So despite the sophistication that you might talk about in these large strain mathematical models, finite strain models and material coordinates and all that, we still are hard pressed for material property relationships and boundary conditions. And we need to be ever cognizant, this is near the end, of undertaking $1 million solutions on a dollar's worth of data. And that's especially true for this. It's all waste. Nobody wants to put any investment into waste material. Just dispose of it. So, thank you very much for your kind attention. I ran a few minutes over, and I apologize for doing that. Thank you very much.
Rather broad presentation. Ready for questions? Part of it raised some questions.
Good question. If I understood you correctly, you said you found little difference in the shear strength between those samples that were dispersed versus populated?
Where the what?
In the samples, you had different samples with dispersed or populated fabric.
Of clay, you're talking about the clays?
Right.
The clay soils, okay.
And you said you found surprisingly little difference in the shear strength.
Well, when you look at a clay sample, and especially it took us many years to develop how to make the damn sample in that slurry consolidometer. And now you've got these you got plates, and looking in you got edges, so you somehow think, darn, if I'm going to test this way and this way, I'm going to get something real different. And you didn't. You got something that was typically 10 to 25% different.
Was that with a vein that you were testing?
Well, it was traxial test, but also a vein. So on the oriented samples, the horizontal vein, assuming so this vein was somewhat higher shear strength than this vein. Okay, that's number one. Random samples were higher than both, either this or this. but not all, I mean, pretty consistently. Creep test, you got more deformation. All this was consistent, and all of it was relatively small values. We were hoping for this could be 3 times the whatever, or 2 times or something. There really some big difference. So in that sense, after 10 or 12 years or whatever it is, and half a dozen theses, and what the hell, all we find out it doesn't make any difference, or it doesn't make that much difference. But that's life, I guess.
Got another loaded question.
How did you measure the hydraulic conductivity in the field with the 2 points that were much bigger?
An infiltration test.
Infiltration.
An infiltration test. Yeah, it wasn't all that deep, probably about 5 feet deep, and infiltration test. Yeah. Well, we also, take it back, so we've ran that, but we also ran some pumping tests. Yeah, we also ran some pumping tests. I'm trying to think where we did those, because out in the field there, you didn't have electricity and so forth. So those, I'm pretty sure those were infiltration tests. But in one of those areas where we could actually, with a long extension cord, got some access to electricity, we did a pumping test. But those were infiltration tests, I'm 99% sure.
And typically, when we see these huge differences in hydraulic conductivity, we attribute this to fissures in the field that don't exist in the lab, but in these very wet materials. So how would you explain this huge difference?
Those tests were conducted in areas where there, if you notice the step diagram of filling, you pump dredgings in an area and you leave it be. You also notice the vegetation, a lot of growth. Then the next year you come back and fill it some more. I think it was the vegetation, the root system and so forth. Yeah, that's what we yeah, and that certainly would explain it. Yeah. Now the vegetation may only have gotten that high, but it's still there.
Then Ray, you showed some increases in strength with time over the slurry that you allowed to consolidate.
Right, the dredge materials.
Yeah, and I assume that in some of those data you also have some way of getting a handle on some description of modulus versus time as well. You ran tests on that.
Yeah.
Did you ever compare the rate at which those increases were occurring with the kind of data that people like Trudeau and Don Anderson maybe about 30 years ago were getting by using cross-hole shear wave velocity tests on plates and looking at what the secondary compression effects had on the shear wave velocity?
Yeah, no, we didn't. We didn't. It didn't look at modulus.
Because what was happening was they were getting, it's been a long time, they were getting pretty significant increases. Something like 30, I think it was 40 per second per decade of secondary compression, which is a lot in shear wave velocity.
We have some pressure wave, or so-called seismic refraction stuff that we have that possibly we could go back, not shear wave, but I know, and these things were so damn wet and they attenuated so fast, we literally were setting off sticks of dynamite to try to develop enough wave to propagate a few hundred feet.
I just wondering if the issue was the rate at which that was happening.
We're concerned about breaching the dam and the dike and have it all of it flow out in the Maumee River and Northwestern gets sued. But that didn't happen, fortunately. No, we didn't do that. That would, yeah.
Got another question here.
Yeah, I don't remember seeing the word or hearing flocculation as it influenced any of those physical parameters that you discussed. Is that an issue?
Flocculation?
Yeah.
In what parameter? The shear strength and that kind of?
Well, any of those properties that you discussed here during the slurry part.
Well, we didn't. The only place we played around with flocculation a little bit is for the dredgings, for example. All important is the rate of sedimentation in those impoundment areas, because in this there was just a weir and the effluent was going over the weir. And there's another whole study which I didn't talk about. It's in the paper. we showed that the effluent was as good as the river water in the Maumee River, so it should be no problem.
The application I'm thinking about is as it affects resuspension and the deposition of dredge sediment within the water column. You can say there's something on that in the paper.
Yeah, well, what's in the paper is that Pen 7, we did a study, I guess it was for 4 months, as the dredge material was pumped in. It sounded, for those of you who don't know how the dredge operates, the dredge scoops the material out of the channel and puts it in the hold of the dredge. And it tries to get it fairly as thick as you can so it can hold as much as you can. Then it pulls up to a pipeline by the disposal area. Now it takes in river water, dilutes the dredgings, and pumps them into the disposal area at about 12 to 15% solids content. Okay? Now that settles with time. I mean, there's several acre. I mean, big disposal. That settles, and the effluent goes back over the weir.
Right. Yeah, I understand that kind of thinking about the development of analytical ways to analyze and predict the effects of flocculation
We didn't play with flocculation anywhere in this project, except the only place is when you run a hydrometer test in the lab and you get the so-called true, whatever that means, grain size distribution of these dredge materials. But we never, that was just for interest, because what we dealt with was whatever came out of the river. We figured it's not dispersed. There's no dispersing agent added when they pump it in, so we shouldn't mess around with it. So I have no data on anything that is not natural, or whatever, natural being as it's pumped in.
Professor Krizek, I appreciate your comments. I didn't want to ask a question, but I have a practical problem that I'm working on. There's a dam up close to Hearne, Texas, about 20 miles north of here. Dam's been in place for 50 years. We had 19-inch rain overnight, and the dam blew out. What was left was pretty much a desert, and it had about 4 to 5 feet of sediment in place that had the consistency of Jell-O. And as you were delivering your talk, I thought about how it might, how I might be able to utilize some of your points in trying to come up with a dam design to replace the one that blew out. And I'm reminded of a comment that my dad frequently made, and that is that soil mechanics is about 50% science and about 50% art. But I really appreciate your comments. I think they're very valuable. And this is a plaque commemorating your talk today and an honorarium. Thank you very much.
Thank you very much.